Hello everyone, welcome back. So today in this video I'll explain that when uh, we apply a AC voltage to a LCR circuit, then what will be its current, or you can say maximum amplitude of current, its phase angle, its relationship between your voltage and current. So all these things we will discuss in terms of Phasor diagram. Already in I think in my previous video I have explained or discussed about when a AC voltage is applied to a capacitor only circuit. If a circuit has only capacitor, then what will be the relationship between your applied voltage and the current in the circuit. So that one I have already explained. So here a series LCR circuit, that means a inductor will be there, a capacitor will be there, and also a resistor will be there, and all the three components will be connected in a series, and we will provide a alternating you can say voltage to the circuit as a source voltage or as a applied voltage. So what will be the behavior of current? So let us discuss that. So let's first draw the circuit diagram. So here we'll provide a AC voltage to the series LCR circuit. Let's say this is your resistor R and a capacitor will be there. These are the symbols of the electrical components, you know that, and there will be a inductor in the circuit, and here we are applying the voltage, and let's say it is a oscillating voltage, it is a alternating voltage. So we'll write EM sine omega t, we'll write like this. Omega t is the frequency, its oscillating part, and EM is the its length, or you can say its maximum height peak of this EMF, whatever we are providing. And this is the sinus, this is a sinusoidal wave. So this is a sine part, you know, it will be oscillating. So we are providing a oscillating voltage, so we are expecting a oscillating current in the circuit, and let's say we will get the current I is equal to, or we can represent with small I Im sine omega t minus phi. Let's say we will get in this, we will get the current. Im is the maximum amplitude of the current, and phi will be the phase angle or the phase relationship between your EMF, applied EMF, and the current I. So with our discussion, or we'll discuss with the Phasor diagram, and we'll find out the relationship between this EMF and your IM. So here what we'll do, we'll draw the Phasor diagram first, and Phasor diagram I'm drawing for that if a circuit is only having a resistor, that is, if I'll provide the AC voltage to a circuit which will have only resistor. For example, if the circuit looks like this, only it will have a resistor only circuit. So this is a resistor only circuit where I am providing a AC voltage to the circuit. Then you know in the previous discussions that in this circuit your current and the applied voltage will be in phase, their phase will be same. So you can say if this is your voltage and same will be the current, the phase relationship will be same for resistor only circuit. And we also know for a capacitor only circuit, if AC voltage will be provided to a capacitor only circuit, then the phase relationship between your voltage and current, that your voltage will be, suppose this is your Vm, your current is lagging behind the voltage, that means this will be the I here, or Im. you can write. So here that will be 90-degree angle between both your I and B will be, this is the EMF, you can say EMF you are applying, or EM you can say. So the relationship between these two, here it is moving ahead of this current, and you can say current is lagging behind in case of a capacitor only circuit. So, and in case of your inductor only circuit, when AC will be applied to inductor only, then you can say if a inductor is there only in a circuit having inductor only, so what you can do here, the relationship between your voltage and current will be here, the if this is your voltage, the current will be ahead 90-degree, so this will be your current. So the phase relationship between voltage and current in your inductor only circuit is ahead of, or you can say current is leading here, or voltage is lagging behind, the applied voltage will be lagging behind the current in inductor only circuit. In capacitor only circuit, the current will be your lagging behind the voltage, and in resistor only circuit, the voltage and the current both will be in the same direction. So if we will include all the three components in a single circuit and connected in a series, so we can write, or we can draw a phasor diagram like this for your LCR circuit. How will you do that? So here what we can do for LCR circuit, what we can do here, the phasor diagram we can draw like let's say this is your VR. For resistor only circuit, the voltage and the current both are same, so we'll write this, we'll do like that. So this is your VR, and here it will be VC, here it will be VL. So inductor only circuit, VL will be ahead of the current, so this is the current, let's say this will be VL, and this is your VC, this is your VC. And if both will be, because VC is lagging behind your VR, and VL will be leading ahead 90-degree, so you can see, you can write, because they are in opposite in direction, so the resultant will be, you can write without writing this one, you can write VL minus VC, you can write this, right? So the resultant of these two vector, let's say will be, let me draw a little bit like this, okay. So let's say the resultant is in this direction, and it will be your EM. This will be the resultant, because in the circuit you see, if you are providing a voltage E, you can write, you are providing a voltage E to the circuit, then this is dropping VR. So from loop law we know that your E will be equal to VR plus VC plus VL. This is from loop law, we know that, right? E equal to VR plus VC plus VL. That means if you will add all the three three drop in potential or potentials in the circuit, then it will be equal to the source voltage or applied voltage. So this one must be the resultant of all the three vectors, that is here it is VC, this is VL. And without writing this, the resultant of VC and VL, I'll write VC minus VL. Again, VC minus VL, this vector, and VR, its resultant should be E vector. Or you can say, you can shift this one here and you can form a parallelogram. You can form a parallelogram so that E will be the resultant one. And of course, as it is leading 90 degrees, so this angle should be also 90 degree. Now, E is a resultant of these two vectors, that is VR, and this vector is VL minus VC, right? So what you can write here? Two vectors 90 degree. If two vectors they are 90 degrees, so their resultant vector is A square plus B square plus 2AB cos 90. Cos 90 is sin 90 is 1, cos 90 is 0, so this one 0. This is the resultant, right? You know from your parallelogram law of vector addition. So here we can write that E is equal to, your E is equal to VR square plus VL minus VC whole square, right? And you can also write that this is your E square. So E is equal to, you can write that is I into R, that is the total current and resistance, equal to VR is your I into R whole square, you can say, and these are VL. You can write as your I into here XL. The resistance here across capacitor will write XL square minus XC square. So if I will take common from everywhere I, so I square will cancelled out. So what I'll get ultimately is, or you can say, you can write this is EMF square. You can write this. So EMF square equal to I square, you can take common here. So you will get R square plus XL square minus XC square. You can write this, right? Or you can write your I is equal to that EMF square by R square plus XL minus, this is L, XL minus, this was a whole square, right? So this was a whole square, this is a whole square, right? So if you want to write that I is equal to E, square will be removed, right? E by R square plus XL minus XC whole square root over. So this is your current. So current is equal to your EMF divided by voltage divided by your R square plus XL minus XC square. And this one is exactly the dimension of your resistance. So you can write that a new variable or new term you can use, that is called impedance. The denominator here is called impedance and is written like this: impedance, that is Z. So Z is equal to R square plus XL XL minus XC whole square root of. This is called impedance. Okay, so the current is the amplitude. This current means this is amplitude exactly, if you say, and this will be your maximum amplitude. So your amplitude Im is equal to Em by r square plus your you can write here. So your Em upon r square plus your XL minus XC whole square, because you can write other term was the, this is oscillating part, this is the magnitude part, so you can take the magnitude, right? So you can say that I am equal to Em by Z also, you can say. So here you are getting one thing, that current is voltage by impedance. Now one triangle also you can make for easy remembering. To remember this thing easily, question comes from this section every time. So you can see, you can draw a triangle, and in this triangle you can or do the triangle like this. This is your phi, and here it is your phi. This is your phi, and this one is omega t, so this is omega t minus phi, and the full is omega t. Full is omega t, right? So this is your phase angle. If this is your phase angle, then what will be tan phi? Tan phi is this by this, right? That you can say tan phi is, this is your x L minus xc, and this is your r, and this is your z. R square plus xl minus, this triangle is called impedance triangle, xl minus xc whole square is your z square. Now you can say tan phi, that the phase angle also is our interest. Our interest is Im and phi. So tan phi is, you can say, xl minus xc by r. So these are the two results. These are the two results of our discussion, that current and the phase angle. Now there can be three cases, like suppose case 1, XL minus XL is greater than XC. You see, if XL is greater than XC, then you will get a positive phi, right? You will get a positive tan phi. If the phi is positive, that means your VR means it will be somewhere lagging, the current will be lagging, right? Here the current will come left side because it's a positive one, so omega t minus phi, it will come, your current will be lagging behind the voltage. Okay, so current will be lagging behind, or lagging, just I'm writing, I will be lagging. So if second case, if XL is less than XC, then you will get a negative phi. For negative phi, you will get this one quantity will become positive. So I will come to the right side of your applied voltage, that is your E. So I will come right side, that means I will lead, or you can say your EMF will be lagging behind the current, right? So it will be, I will be leading. Now third case, XL equal to XC. If both your XL and XC are equal, so it will be 0. So tan phi will be 0, that means phi is 0 degree, that means both current and voltage will be in phase, same phase, right? So if current is this, voltage will be like that, so there will be a resonance. In this case, when XC equal to XL, this case will be called resonance. That we will discuss resonance and sharpness, Q factor, all these things we will discuss in the on the next videos. So when XL equal to XC, resonance will take place, that is in phase. I will be same with the B, so that will be in phase. So it will be in phase. XL equal to XC, that will be in phase. And you can say XL is what? XL is your inductive reactance and XC is capacitive reactance. What is XL and XC? You should remember this. XL is inductive reactance. This is inductive reactance, and XC is capacitive reactance, and all these are in the same dimension of your resistance. So this is capacitive reactance, XL and XC. This is L, it looks like C. Okay, so now here we can say when they are in phase, we'll discuss in the next class, resonance will be there. Resonance means you will get a maximum peak. I and B both are in same phase, so if resultant will be higher peak, so you will get a resonance. Okay, so resonance condition is XL equal to XC. XL, you should know, XL is what? Omega L, and XC equal to 1 upon omega C. 1 upon omega C. Let's say these are the natural frequency, omega 0. So you can say, you can cross multiply that omega 0 square equal to LC, or you can say your omega 0, your frequencies would be 1 upon LC root over. Very important relationship for your exam, right? For resonance, a circuit, when it will be resonance. Now resonance you will get when your frequency will be equal to root over of LC, or you can say omega L equal to omega C. At that case, resonance will take place. That means I will be in same phase with the applied voltage, so that you will get a higher current. Like it is having a lots of use in your television broadcasting and all these things. They use the resonance to means for different channels we have different frequency, and they resonate with each other, and we get a clear picture out of that. So that is a electronics communication technique. Sometimes later we'll discuss. So here you just try to get that this should be the resonance condition, and these are the important factor. And we have discussed all the solutions here in phase diagram method, or you can say we have discussed this thing in Phasor diagram method. This is a Phasor diagram method. Phasor diagram method. Okay, and analytical method is also there. Like I can write a differential equation for that, and I can solve the differential equation assuming a solution, and I'll get the same thing. So I can do that also in some other class. I'll also do in that way also, and in next classes I'll solve some questions, and Q factor, sharpness of resonance, all these things we'll discuss. So let's stop here. See you in the next video. Bye bye.